Thank you, Professor, and thank you for the introduction and inviting me to give talk in your seminar series. So this talk is based on three papers which I and Ganesh have published in recent years. So we'll discuss identification problem for time scale setup. So first we'll discuss basics of time scale theory, and then we'll move to the problem discussion. So we know that this that modeling is a very important field, and many times we use mathematical model to represent several phenomena in physics, biology, and economics. So these systems can be modeled mathematically using dynamic equations, which actually describes how the variables of the system changes with respect to time. And many times the differential or difference equations are used to model such most of the processes. And of course, there are other equations as well. Okay. And then so one such example is motion of pendulum, which can be modeled using this second order ordinary differential equation with these are the variables. And then another such model is growth of saving account, which can be modeled using difference equation. So where R is the interest rate, and if AN is the balance in someone's account at the end of the year end, then one can use this under, of course, under very ideal assumptions. Then this model can represent the growth of a saving bank account. And also there is one species which is cicada, and it has a very unique life cycle. So just this example is just to illustrate that many times that R set of real numbers, which is corresponding to the differential equation, are set of set which is integer, which corresponds to the difference equation, may not work. Sometimes we may need some other set, and then the dynamic equation on time scale will play a very crucial role in modeling such kind of phenomena. So in cicada, it has a very unique life cycle. So the lifespan is actually 13, 17 years, and the population is actually affected by both rate of reproduction and rate of mortality. And it actually, for certain period of time, it is underground. So if we want to model this, then we need a set which is a mixture of discrete points and an interval. So in that case, if we define a differential or difference equation, in this case, then we need time scale calculus to model. So time scale has certain application for such kind of species or such kind of phenomena processes. So this is a very emerging field, and it can, and still it's many people are working, and several applications are coming out. So it has a lots of potential. Uh, so let us define the inverse problem. So this is a very general definition. So so suppose we have two topological space x and y, and f is a function from x to y. Then the forward problem is that given input x, if you want to compute y, then this is a forward problem. Inverse problem is if given output y, then if you want to recover the input x, then that is called the inverse problem, right? And so suppose this y from y is given, and we want to find an x solving this equation. Then the key challenges to solve such equations are existence, uniqueness, and continuous dependence. So these are the challenges. And then in sense of Hadamard, we call a problem well posed if it satisfies these conditions that for all y there exists uh, x solving the problem, which means there exists a solution, and the solution is unique, and the mapping is continuous. And then the ill-posed inverse problem is if at least one of the conditions are not satisfied, then the problem is ill-posed. And most of the inverse problems are basically ill-posed. So these are some examples that the multiplication division by a small number a. So the first problem is well-posed, and the second one is ill-posed, because if the small change in a will result a large change in q because of this division by a. Similarly, this problem, the integration problem is well-posed, and the second problem qx is f prime x is actually ill-posed. We can see that this small change will result a huge change, and also uniqueness is also lost. So these are some examples, and now so in and the reference is given below. So these are taken from some from these works. So, and this is one example. If you consider this matrix equation, AQ is F, and the rank of A is defined by minimum of Mn. Then, if M is n, then we have a unique solution for any F, and the inverse operator exists, and inverse operator is also bounded. So, in this case, all three conditions of well-posed in the sense of Hadamard are satisfied. But we can see that in this case, the small change in Q, if you compute, so if you perturb Q by Q plus delta Q, then we get this A Q plus delta Q is F plus delta F. And if we compute the norm of del Q, we get this relation. So in this case, the estimate for the relative error of the solution is given by the norm of delta Q divided by norm of Q, which is less than equals to norm of A inverse, and norm of delta F divided by norm F. We can see the system with incondition matrix. So this is actually stable because this can be a very large. So in this case, the perturbation can result a huge variation in the solution. So the formally, in the sense of Hadamard, this problem is well posed, but but we have this issue with the estimate. Now, if let us define the identification problem, which is suppose we have a function from x cross z to y, and where x z y they are topologically spaced. So these are some problem which are considered an identification problem. So given yz, this pair in y cross z, we want to determine x solving this relation. And we can also pose the problem as given y in y, want to determine xz from x cross z, solving this with additional information that g of xz is equals to omega. So now, the basic of time scale, I'll just cover quickly. So time scale, as we know, is the non-empty closed subset of the real numbers. And some examples so standard examples are R and Z, and then there are other examples that Q to the power and not. And then these sets, Cantor sets, they are some examples of time scales. And these are some examples which are not time scale. So, and these are some important terminology which we will use in our results. So the forward jump operator, which is defined by sigma from T to T, is defined as infimum of all S in T, such that S is greater than T. Similarly, backward jump operator is defined by supremum of S in T, S is less than T, and it is denoted by rho of T. And greatness function is defined by sigma T minus T, which is denoted by mu of T. And of course, in this case, it is assumed that infimum of phi is supremum of T. So, and this is these, and if rho T is T, if T has a maximum T. So these are this. And then these are some classification of points in time scales. So like the point is right is scattered if sigma T is greater than T, left is scattered if rho T is less than T, similarly right dense if mu T is 0, left dense if rho T is T, isolated if T is between rho T and sigma T strictly, and dense if they are equal. So and we can just check with T equals to R and Z. So for T is R, sigma T is T, rho T is T, and mu T is 0. t is z, we get these sigma t plus 1 and mu t is 1. So these are just to some computation. And similarly, these are the concepts corresponds to continuity and some important function in time scale. So in the continuity is called RD continuity. The function is called RD continuous. If it is continuous at all right dense points in T and a left-sided limit exists at all left dense points. And then a regulated function is defined uh, for that if for all left dense point a left-sided limit exists and for all right dense points a right-sided limit exists, then the function is called regulated. And tk is a set which is we remove if t has a left scattered maximum m, then tk is actually t minus m. So we remove m, otherwise tk is t. So, and then the derivative is defined through this, which is called the delta derivative. So, this time scale derivative is, so number is called the delta derivative of function f at a point uh, t in tk if for any given epsilon positive there exists a neighborhood which satisfying this condition. And if f is a function for t to r, and if it is delta differentiable, then we have this relation that f of sigma t is ft plus mu t f delta t, which is the derivative. And this is just to illustrate that in certain cases, when t is r, it coincides with the usual derivative. When t is z, then it is a difference. And for other cases also, these are some derivatives, computation of some derivative. Now, the function is also called pre-differentiable in a given region T, provided that D is contained in Tk and Tk minus D is countable and contains no right scattered element of T, and F is differentiable at each T in D. So, and this is the existence of pre-antiderivative, this result in time scale, that for given a regulated function f, there exists a function capital F, which is pre-differentiable, which means f del t is given by f of t, small f of t. And then one can derive the Cauchy integral formula. So these are standard results that this integral a to b ft del t is given by f of b minus f of a. And these results are given in Martin Bohner's book, which I will give reference at the end. So in this case, one can also evaluate this a to the power t del t. And in this case, this is the value. And this integral is actually, one can compute for certain special functions. Now, if f is an RD continuous function and a, b are elements of T with a less than b, then a, b subscript T actually consists of only isolated points. Then in this case, we have this formula for the integral. And for T, a bounded time scale, if we assume that the set of RT continuous functions just we denote it by CRT0, and then this is the norm which is defined on this set. So and then and these are some key concepts like forward jump operator which we have defined. So this we have just written in a table. Now the solution of unique solution to the initial value problem, which is y del t is pty with initial condition yt0 is 1, is actually called the exponential function in time scale, and it is denoted by ep this t0. And then any n cross n matrix valued function a defined over a time scale t is called regressive if this I plus mu t a of t is non-singular for all t in tk, and I is actually identity matrix here. So in this case, for if we pick T naught in T and A, if we choose from this set regressive function or a regressive matrix set, then the matrix exponential, which is denoted by E capital A T T0 on T is actually defined by this, which is a unique solution of the matrix differential equation. And so we are interested in studying identification problem on a time scale. And if we go back to the history, then it actually introduced by Stephen Hilger in his thesis, and the main aim is to unify the continuous and discrete case. So Professor Albeck, who supervised thesis of Stephen Hilger, he points out that the main purpose of to develop this time scale calculus is unification, extension, and discretization. So this is the main aim to develop such theory. So and for as far as inverse problem or identification problem goes, so not much work is available actually in this direction. So in this work, we tried to solve some basic time scale problem, and which could give a direction to extend our work on more sophisticated or more general problem. So in first, we consider this equation, which is given by, so this is nth order linear dynamic equation, which corresponds to nth order linear ordinary differential equation. So in this case, f and pi's are RD continuous functions from T to R, and del n denotes the nth derivative. And then, so this is the equation which first we want to discuss. In this theory of linear dynamic equation and time scale, the various problems are considered to determine the function y when the coefficient pi and the function f are known. So this is the forward problem, that given these pi's and f, people have discussed the existence and other things about the solution. Now we are interested in the inverse problem, and this work is published in this paper, which is published in Mathematical Methods in Applied Sciences. So we are interested in these two problems, that given a specific solution yi or additional information about the solution, can we determine the function f? And given knowledge of the function f and some information about the solution, can we determine one or more unknown coefficients pi in equation 3? So these are our aim. Now let us assume that all the coefficients are given, and the function f, which needs to be determined in equation. So if a certain solution yj is provided in the additional information, then f can be determined uniquely. Now this can be done by substituting the solution yj in the equation, and we get the function f of t through this, if we know this, if we can determine this. So for each solution function yj, we have a unique solution for the inverse problem in this case. Now, if we change the known solution, then how much change will we get in the solution f? So this is the one question which the answer is given, or it can be given through this stability estimate. So given f1 and f2, if t is a bounded time scale and p1, p2, pn's are constant coefficients, because we are now here we are taking this as constant. And then if y1, y2 are solution to the linear dynamic equation on time scale t, then we have this following estimate. That norm of f1 minus f2 is less than some constant k times norm of y1 minus y2. So this is actually a stability estimate. And now we consider the case when all the coefficients pi's and the function f are unknown. And in this case, this is the existing and uniqueness reserve. So if y0, y1 to yn are known solution of our problem for a time scale t, satisfying these relations, that Wronskian, so W denotes the Wronskian, W of y1, y2, yn at t0 is non-zero, and W0 del I T0 is 0 for I0, 1 to n minus 1. Then the RT continuous regressive functions Pi and F are determined uniquely. So this is the result. We explore this through examples, because it will be clear in that, because the step will be clear in the through examples in the proofs. So let us assume that we have a second order linear dynamic equation, and we assume that the coefficients P0 and P1 are unknown, and we want to determine them using some information. And the unknown coefficient can be determined using this characteristic equation, lambda square plus P1 lambda plus P0 is 0. If we know all the roots of this characteristic equation, we can determine P0 and P1. So in order to uniquely determine the solution, the known solution must contain information about the roots of the characteristic equation. So let us pose this problem. So consider this initial value problem involving a first order linear dynamic equation with RD continuous coefficients. Y del t plus pt yt equals to 0, and t is in t, and y at t0 is y0. So suppose we are given one additional information that y at t1 is y1. Then we want to determine the regressive RT continuous coefficient p for our initial value problem. So this we can achieve through this. So any solution we know that can be written in this form, right? So the solution yt is given by this exponential function ep tt0 y0, given y0 and t0. And with additional information, we have this that ep t1 t0 y0 is y1. Now, any solution of system 10 and 11, this the above two system is also a solution of the system 7, 8. So that is well known because it's satisfying this condition. If we substitute, we get the equation. So therefore, these two systems are equivalent. Now we'll validate the theorem by choosing some particular functions and for arbitrary time scale. So let us assume that y0 is given by this and y1 is given by this e2 tt0 plus half e4 tt0, and then y2 is given by this. So these are the solution of this following time linear dynamic equation on time scale, which is second order with p1 at coefficients are at p1, p2, and f. Now p1 and p2 and f are regressive functions from t into r, and I want to determine the coefficient p1, p2 and the function f using these given information. So first we want to determine p1, p2, and so we can differentiate y0, y1, y2, and the delta derivative is given by this of y0, of y1 and y2. Now we can check the condition of the theorem. So y0 at t0, one can check, is actually 0, and y del at t0 is also 0. And the Wronskian W of y1, y2, t0 is actually 3 by 2 in this case, which is non-zero. So all conditions of theorem are satisfied. And then the claim in theorem is that it must have a unique solution, right? So in this case, we get a unique solution, which we can actually, here we can compute. So we can define this function v1 and v2. So v1 is y1t minus y0t, and v2 y2t minus y0t, which is given y1 and y0 and y2. We get these values, and then we compute the delta derivative of v1, v1 delta, v1 delta delta, and similarly v2 delta and v2 delta delta. So this, if we substitute in our equation, we get these values, and which can be written in this form for P1, P2. And this we can solve. And this system is, we can use the elementary row transformation, and we can see that the linear system is actually equivalent to this system, which gives the solution P1t equals to -5 and P2t is 6. So we can determine these two using this information, and the solution, and these are the solution. And so we can substitute, we get this equation, linear dynamic equation, and then we can compute f of t by using this information P1 and P2. So f of t is actually given by this, and which in this case we comes out to be this value. And similarly, so we have found all unknown coefficients in this case. So in this case, our linear dynamic equation on time scale is given by this y del t minus 5y del t plus 6yt is equals to E4tt0. And this example is actually motivated by this problem 2, example 3.74 by Martin Bonner and Alan Peterson's book. So they have solved the forward problem and we have solved the inverse problem, and it matches with the solution actually matches. And now the following problem also we can pose as inverse problem. So suppose we have y0 equals to 1 in the equation, and t, the time scale, we choose as n0 square. So it's 1 square, 2 square, and 3 square, these points. Then in the inverse problem, which we discussed, we want to determine a regressive RT reverse coefficient P, which is defined from T to R. So in this case, we have this following initial value problem: y del t plus pt yt is 0, with y0 is 1. And we can write down the equation. And since we have chosen a particular time scale, so in this case, the goal is to determine the coefficient P. And we have this relation that integral T0 to T1 of this is equal to log of y1 upon y0. We can, if we pick these values, then the corresponding problem is this, and which can be solved for our time scale. So in this, we have this point 0 only in that intersection with t, and it comes out to be mu 0 times log 1 plus mu 0 p0 upon mu 0 equals to log 2, which if when we solve, we get p0 equals to 1, which actually matches with the values in the forward problem. So in this case, we get pt equals to 1 for t in 0, 1 intersection t. Now, suppose we have one additional information that y4 equals to 8 instead of y1 equals to 2. In this case, the corresponding equation is given by this, and we get this value after simplifying that 1 plus p0 plus 3p1 plus 3p0 p1 is 8. And this has two pair of solutions. And we can see that one also solved this problem. So which means we, for other information also, we are getting the value 1. The other pair is also 7, 0. So so in this case, we get more than one solution. Now, if we consider as time scale 2 to the power n naught, and if we assume y1 equals to 1 is our time scale. So in this, for this problem also, we can pose an inverse problem that whether is it possible to solve this inverse problem or of determining the matrix A given several solutions y to this problem 15 are given any additional information about this solution. So we want to discuss this as well. This paper is published in the Journal of Analysis. So we can, if we consider this problem, y del t is AT yt, and we want to determine the regressive matrix valued function A from T into MNR, which is set of matrices in the system if R many solutions are known. And this system is given by this. Now, if R is n, then and given y1, y2, yn are linearly independent solutions, then the matrix valued function A is determined uniquely. If R is less than n, then there exists more than one matrix valued function A solving the inverse problem 14, which is defined previously. And this we again illustrate by considering this example. So suppose we have this system, y del t is AT yt, and we assume that y1t and y2t are solution to this system. And we want to determine A given these y1 and y2t. So in order to determine this, we first compute the determinant of this wy1, y2t, and which is non-zero. So this we can take, and then which means the solutions are linearly independent. Now W del T is actually given by this matrix. So we can compute the delta derivative. So AT is actually can be computed through this, which is given a W del T, WT inverse, which after computation we get this value for this setup, that 3 minus 1, 5 minus 3. Now, so we can see that y1 and y2 are actually solution to the linear system y del t is a yt. The matrix A is given by 3 minus 1, 5 minus 3. So we have determined the matrix A in this case uniquely. Now, if the second case where R is less than N, so in this case, let us assume that we have only one solution, and then we just pick 0, 1. So we can define this matrix, and W del T we can compute, which is given by this. The inverse is given by this, and then AT can be computed using the same formula because we have this relation for W. So if it comes out to be 2, 2, 0, 0. So for this solution, we are getting this matrix, and the previous matrix is also a solution, which also has a solution, right? This one has a solution. So which means in this case, the matrix is not unique. So A2020 also gives this solution, and the previous matrix also gives this solution. Okay. So these are just to illustrate that in this case, we do not have unique solution. Now, this problem is to determine the regressive matrix valued function A for this non-homogeneous system dynamic equation. So we have this equation y del is ATY plus f of t, and y1, y2, yr are solution to the equation, to this equation. Now, we assume that R is n. Then in this case, if the determinant of y1, y2, yn is non-zero, then there exists a unique matrix valued function A solving the identification problem defined above. And this we can pose this problem for this special kind of information. So we want to determine a function and a real number lambda satisfying this. Y del t is lambda a yt, and yt0 is y0, and with this additional information that this inner product b of yt1 is alpha. Now we need to determine these y and the real number lambda if the matrix A is symmetric. So in this case, we choose the matrix symmetric matrix, and we discuss this problem. So in this case, we get this relation where HITT0 is given by this integral, and the lambda can be determined if a solution exists from these relations. And then once we get lambda, we can determine the function y. So this we illustrate again with one concrete example. So if we choose y0 is 2, 0, and b is 1, 1, and t1 is 2, and alpha is 8, then we can solve the corresponding inverse problem on t equals to z. And in this case, we want to find a positive real number lambda and a function y. So the problem is in this setup for this choice is given by this y del t is lambda 3 minus 2 minus 2, 3 yt, y0 is 2, 0, and the inner product of this vector 1, 1 with y2 is 8. And in this case, we get yt is e lambda a t0, 2, 0, which is the solution of this, where a is given by this matrix. Now we want to find y of 2, and we can so y of 2 is given by e lambda a 2, 0. So we need to compute e lambda a 2, 0, which is given by this value. And therefore, y2 is given by this column matrix. 26 lambda square plus 12 lambda plus 2, and then the second is minus 24 lambda square minus 8 lambda. So now we can use the additional information which is given by the inner product of this vector y1, 1, 1, and y2 is 8. And this gives this equation which we can solve, and we get these two values of lambda, which is 1 and minus 3. So we are interested in positive lambda. So lambda 1 we choose, which is the required solution in this case. And once we have lambda equals to 1, we determine, so we can determine the function y using this value, and then y del t is actually given by this 3 minus 2 minus 2, 3 yt, and y0 is 2, 0. Now, this initial value problem, we have unique solution, which is given by yt, e1 t0, 1, 1, plus e5 t0, 1 minus 1. Now, we also define this following ill-posed problem on a general time scale t. So we want to determine the regressive matrix A, which is 2 cross 2 matrix defined over R, and a function Y, uh, which solves this following linear dynamic system of dynamic equation given by Y del T equals to A of YT for all T in T, with this initial condition that YT0 is U, and satisfying the additional condition that Y at T1 is V and Y at T2 is given by W, where these are in R2, and we assume that TH is not equal to TK for HK is 0, 1, 2, and H is not equal to K. So this problem we solve under this condition. So if A has two coinciding eigenvalues, let us say lambda equals to lambda 2. So in this case, this determinant of A, which is given by trace of A square minus 4 times determinant of A. So this del A, this value is 0, and we get this relation corresponding to this. So the solution to our problem is given by yt, which is u1 e lambda 1 of this vector plus u2 e lambda 2 in this vector, and subject to this condition where ft t0 is given by integral t0 to t del s divided by 1 plus lambda 1 mu s. And we can write down the corresponding equations, and which is, these are the equation which we can solve in order to get solve our problem. So these are the set of nonlinear system of equations, and the function f t t0 is given by this integral, and this is the case when A has repeated eigenvalues. So this we can summarize in terms of a theorem that if the matrix A has coinciding eigenvalues, then a solution to the problem is actually given by these equations, subject to the condition that A12, A21 is less than or equal to 0. Because we want that del A to be 0, and because the first term is positive, so we need this condition. So we can consider this problem just to illustrate. So suppose we want to identify the parameters alpha, beta, and a function y, uh, uh, which is C1 function, 22R, by solving this following dynamic equation and time scale. So y del is ay, and y at S0 is given by some C1, C2, and the matrix A is given by this 0, alpha, minus 2, beta. And we solve the problem of identifying the parameters alpha and beta on the time scale R and Z with the initial condition y0 equals to 3, 4. So in this case, we get, if we choose this time scale as R, then we actually get these equations, relations. Yt is given by these with additional information that y log 2 is 812, and then we get the following system of nonlinear system of equations. So these are the equations, and we can get some by just looking and using some tools. You can see that alpha equals to 1 and beta 3 satisfy the equations, and these are the one possible solution. There can be other solution, but this is one solution. And therefore, in this case, A is given by 0, 1, minus 2, 3. And also lambda 1 in this case is 2 and lambda 2 is 1. And after substituting these values of lambda 1 and lambda 2 in the equation, we get yt equals to this. 2e to the power t plus 2e to the power 2t and 2e to the power t plus 2e to the power 2t. So, and if t equals to z, then with the additional information, y1 is 7, 10, we obtain these systems of nonlinear equations, which we can see that we have this lambda 1 equals to 2, lambda 2 equals to 1, and then we obtain alpha equals to 1 and beta is 3 in this case. And we get this matrix and yt, which is this solution in this case. So these, and then we can also take with this example where we want to identify the regressive matrix A, which that has geometric multiplicity 1 and a function y which solves the this vector dynamic equation. Y del t is A of yt, and y0 is given by 1, 1. and they satisfies this additional condition that y4 is given by 2 to the power 8 1 1 and y minus 4 is given by this. So in order to solve this, again, we need to solve the system of nonlinear equations, these, and subject to this condition that a21, a12 is less than or equals to 0. And we can see that a11 is 2, a12 is 1, a21 is minus 1, a22 is 4, satisfies these equations. And hence, in this case, the matrix A is given by 2, 1, minus 1, 4. And if you substitute this in the equation, we get this equation y del t is 2, 1, minus 1, 4 yt, and we obtain yt is equal to 4 to the power t y1, which is a solution in this case. So we can recover both in this case. Now that's all, and these are the references. Uh, so these are some important books and papers in the theory of time scale. And so the lecture is mainly the prerequisite and the literature is taken from these. And these are the papers which we have in which we have worked on these kind of problems. So this one is in ACTA applicanda math and these two papers. So that's all. Thank you everyone for attending. If you have any questions or any discussion, I'm happy to answer.